I'm missing this thing entirely. Thank you. So is this on? Sound? 1, 2, 3. Perfect. All right. So, morning everyone, and welcome to edition 2 of Convolutional Neural Networks. Wait, doesn't this work? I've got to switch it on. How do I switch this on? Ah, perfect. Thank you. So, in the last class, we just sort of built up the idea of convolutional neural networks from scratch and saw that, wait, do we have the pens, the black pens? Yeah. Perfect. So, and we saw that that the network, or the convolutional neural network, is basically derived from scanning an image, data of any dimension, and the dimensions in which you actually scan the data can differ from the dimension of the data itself. So you could scan images in 2 dimensions. You could scan a spectrogram, which is actually a 2-dimensional image, along 1 dimension. You could scan a block, which is 3-dimensional in 2 dimensions. You could scan a 3-dimensional block in 3 dimensions, and so on. But the original model wasn't derived from the point of view of trying to scan an image and sharing parameters. The original model owes its existence to cats and an attempt at understanding how human perception works. So the story so far, we saw pattern classification tasks such as does this picture contain a cat, or does this recording include the word hello, are best performed by scanning for a target pattern. The scanning an input with a network and combining the outcomes is equivalent to scanning with individual neurons, where the first level neurons scan the input, the higher level neurons scan the maps formed by the lower level neurons, and there's a final decision unit or a decision layer which takes a decision. Now, deformations in the input we saw could be handled by stuff like max pooling. For 2D or higher dimensional scans, the structure was called a convolutional network. For 1-dimensional scans along time, this was called a time delay neural network. But then, where did this model actually come from? It wasn't derived from the scanning perspective. It actually starts with this, trying to understand human visual perception. The story goes back many decades. How do animals see, right? How exactly do we perceive our world? How do we interpret the visual stimuli that go into our eye? Now, early on, all of these analyses were based purely on behavioral response. What do you see and how do you interpret it? So these things, for example, these were very popular items of study in early research. This is what is called Gestalt. Now, the figure to the extreme right, what do you see? A sphere, right? With spikes in it. The next one is it's a panda. Does anybody see the dog in the third one, right? And the fourth one, what is the one to the extreme left? Cube. None of these objects exist, right? There is no cube. All you have is a bunch of circles with a few holes in them. You don't really have a dog. You just have a bunch of patches. Your brain cooked up the dog. There's no panda. There's a bunch of patches. Your brain cooked up the panda. And there's absolutely no sphere. There's just a bunch of triangles. But somehow we began filling in the additional detail necessary for us to make sense of these images. And we saw things that weren't there. So a lot of this whole theory of Gestalt. The brain has an innate tendency to organize disconnected bits into whole objects. The early study in visual cognition dealt with behaviors and phenomena like these, but there was no real understanding of how the brain itself processed the images. What was the signal processing? What was the what was the signaling that was going on inside the brain. So the first guys to study these were a guy called Hubel and Wiesel in 1959, and they performed a pretty nasty experiment. It started with cats. So this was the first study on the neural correlates of vision. This is a paper called Receptive Fields in the Cat Striate Cortex. The striate cortex is a portion of the brain where you actually the neuronal patterns actually occur in stripes, so it's striated. It corresponds roughly to the V1 visual cortex. Now, our visual cortex, the portions of the brain that interpret images, are sort of divided, by people who study these things into 7 areas, V1 through V7, where each layer, each V, works on the interpretations of the earlier V's and makes more and more complex hypotheses. So the striate cortex is approximately equivalent to the first visual layer, V1 cortex, which forms the first level impressions. Now, for this study, they actually got a bunch of 24 cats, anesthetized them using truth serum, which is sodium pentothal, immobilized them, put them on artificial respirators because if they didn't, they would die, and then they stuck electrodes into their brain. Now, after all of this, they don't actually tell us that the cats survived the experiment, but they do tell us that afterwards they studied brain tissue. So they leave the rest to your imagination, right? So here's what they really did. They stuck these anesthetized and effectively dead cats and opened kept their eyes open, and incident light of different wavelengths on the retina through the fully open iris. They also relax the iris. Now, what this does is as soon as light falls on the retina, it's going to stimulate the nerves behind the retina. So it defines the immediate 20 millisecond response of these cells. And then they beamed light of different patterns into the eyes and measured neural responses in the striate cortex. So here's a typical setup. This is actually from their paper. They have the poor cat stuck over there with its eyes open. It's not really awake. It's possibly not even alive. And then they have these little electronic gizmos in front of them, which just beams out light with the light in different patterns. And here's what they found. So they beam these patterns, different visual patterns, into the eye and figure out when any specific neuron fires. And they found that neurons had responses like these. So the neurons would fire only if light of each neuron would respond to light of a specific pattern. Now, each neuron had, if you just had uniform light over the entire visual region, the neuron wouldn't fire. On the other hand, if you had very directed patterns, the neuron would fire. Specifically, they found that the neuron had inhibitory and excitatory regions. So what this means is that there were regions where if light was incident, this would actually inhibit the firing of the neuron. There were other regions where if the light was incident, this would excite the firing of the neuron. There were other regions where the neuron would not respond at all, right? So, and typically these inhibitory and excitatory regions sort of alternated in a very interesting way, somewhat like those. So those figures are from monkeys and from mice. But you see what happens over here. The neuron in this case does not fire if the light falls in the blue region, but it does fire if it falls in the yellow region. And what does it show? It's actually got a response which kind of peaks at some point along the line, right? So they found that a light stimulus covering the entire receptive field or diffuse illumination of the whole retina was ineffective in driving most units. Lights must fall on excitatory regions and not fall on inhibitory regions. That is the only condition under which the neuron fired. And they found that now the response, or each neuron responded to a specific pattern of light. So they call the specific pattern of light to which the neuron responded the receptive field of the neuron. So the receptive fields could be oriented in vertical, horizontal, or oblique, or in an oblique manner. And instead of having an entire line of light, if you just took a single spot and moved it around, the neuron responded to movement in some directions more than others. So here are the kinds of responses they find. These lines show the spiking response of the neuron. the figure to the left shows the kind of light that's incident on the retina. And so if you start off with a horizontal line and then you keep rotating it around, you find this particular neuron fires most when the line is perfectly vertical. And then as the line continues to rotate, the neuron stops firing. Then if you, instead of having an entire line, you just have half a line and this thing rotates around, you find essentially the same pattern. The neuron only fires when the light is horizontal and not when it's vertical. In this case, the figure to the right is actually the motion of a single spot. So you can see that neurons seem to be responding to certain orientations of light. So the conclusion they had was that oriented slits of light were the most effective stimuli. And later, they also identified, this was the first conclusion they had, but then they went on to build on it and they tortured more cats. And they showed that within the striate cortex, you actually have two levels of processing. The first is what they called a simple, the response of something called simple cells or S cells. And the second level of processing was performed by something called C cells or complex cells. Now, both of these responded to oriented slits of light, but then the simple cells would respond to lights in certain orientations, but they would get confused by noise. The complex cells would look at groups of these simple cells and vote across these simple cells. And so they sort of cleaned up the response of the simple cells. So here's what they find. You'd have groups of simple cells of this kind. Each of these simple cells might respond, for instance, to a diagonal line, but they also tend to have a characteristic of responding to some noise. So then you have the complex cell, which looks at multiple of these guys, maybe 3 of these together. And based on whether they're all, whether the majority of them are firing or not, it would fire. So it would depend on, so the complex cell was effectively cleaning up the noise response from the lower simple cells. So the complex cells built from similarly oriented simple cells, number one. And number two, there's a complex buildup. As you go through these, the complex cells feed to other simple cells, which feed to other complex cells, and so on. So successive transformations through these simple and complex cells actually showed response to more and more complex patterns. And later on, they actually went on to work with monkeys, at which point you don't really want to read more papers. So let's go back to the basic problem itself. So they have actually, there's a nice little concept that they have come up over here, which is the nature of the response. Anyway, it's a very nice paper, right? Unfortunately, it's also a very sad paper. All they have actually managed to show is that anesthetized cats have a certain kind of response when a certain kind of light is incident on their not so waking brains. So whether that actually translates to real human beings, to real animals and other conditions remains unknown, and this is work in progress. And here's adding insult to injury. It says this model cannot accommodate color, spatial frequency, and other features to which neurons are tuned. The exact organization of all of these cortical columns within V1 remains a hot topic of current research. So I'm not really sure what was eventually proved by those papers, but that did give us a very nice computational model that we could work on. So fast forward to 1980 from 1959. This is Fukushima, Kunihiko Fukushima. I don't think that's quite his picture from 1980. I think that's more recent than that. But then he computationalized the Hubel and Wiesel model. He also observed deficiencies in the model. First, there's position invariance of the input. There's something that's called a grandmother cell. Have you guys seen this article about the Jennifer Aniston cell? Seriously, right? So they have many of these neuro experiments are performed on epilepsy, patients with epilepsy. So these guys are lying around in hospitals with their skull opened, and they are treating the lesions or whatever. But now, because these guys are just lying there with their skulls open, they can actually put these little mats of many electrodes on the head and measure neural responses of individual brain neurons to different stimuli. And they found that one of these characters had a neuron that would only fire if he was shown a picture of Jennifer Aniston. Nothing else, right? So this was a Jennifer Aniston cell. This was a paper many years ago. I think it was in Nature. There's nothing special about Jennifer Aniston. It's just that, you have different neurons responding to different things. And So the typical example they give is your grandmother. There is a cell in your head that responds when it sees a picture of your grandmother, or when it sees your grandmother. This is your grandmother cell, or maybe there are multiple of these. Now, what Fukushima realized was that, realized was that your grandmother's cell is going to fire regardless of whether your grandmother is to the right of your vision or to your left. It's going to respond to your grandmother, not to your grandmother standing in a specific position, right? And this simple characteristic was not actually being captured by the Hubel and Wiesel model, which said that each of these, you have all of these complex patterns that are detected by neurons, but the fact that this position invariance was not something that was actually analyzed. So Fukushima's model adds on top of the Hubel and Wiesel model and introduces, it actually computationalizes the entire model, but also introduces the notion of position invariance. So in his model, the visual system consists of a hierarchy of modules, each comprising a layer of S cells followed by a layer of C cells. Observe that these S and C cells are following the same model, the same organization that was proposed in Hubel and Wiesel, right? So you can number them like, so U0 is your retina. This is where you have RGB responses. Subsequently you have the first simple layer, US1, followed by the first complex layer, UC1, followed by the next simple layer, US2. US2 gets inputs from the second simple layer gets inputs from the first complex layer. The nth complex layer gets inputs from the nth simple layer, and the nth simple layer gets works on the outputs of the n-1th complex layer. Of these, only the S cells are plastic. So again, this is going back to the original observations of those guys, that you have one set of cells which learn to respond to a certain kind of stimulus, and a second set of cells that cleans up the response of the first set of cells. So in this model, the S cells are plastic, they are learnable. C cells are fixed in their response. Their only job is to clean up the response of the S cells. So S cells respond to the signal in the previous layer, C cells confirm the S cells response, right? So here's how they organized it. Each simple complex module is organized in a layer of S cells and a layer of C cells. So this is the layer of S cells, the first layer of S cells, the first layer of C cells. Now the S cells are organized in many rectangular groups called S planes. So this entire thing is an S plane, and this entire thing is an S plane. And here's the key part. Within an S plane, all neurons have exactly the same response. So C cells are similarly organized into C planes, and now there's one C plane per S plane, and once again, within any particular C plane, all cells have the same response. So the way Fukushima originally set it up, each neuron in the S cell in an S plane would look at an elliptical region of the outputs of the previous layer. So if you were looking at the very first S plane, each neuron over here is going to look at an elliptical region of the retina. Each neuron in the C plane is looking at an elliptical region in the S plane. And observe that all of these guys, so you would have some neuron over here looking at some elliptical region of the S plane of the retina. There'd be a corresponding neuron in the first S plane of the 0th layer or the first layer, right, looking at the same elliptical region. So what we have is that you have this first S layer comprising of several planes. All the neurons in this block have the same response. All the neurons in the next block have the same response, and so on. But the neurons in individual blocks have different responses. And the same thing with the C planes. And now, here's the complete network. U0 is the retina. And then you'd have the first S plane, first S layer with many S planes, each of which is looking at the entire retina, right? Then you have the first C plane, where you have each plane looking at the corresponding S plane. Then you have the next S plane, but see something different over here. each neuron in the S plane is looking at all of the neurons, all of the C planes from the previous layer. So the way he set it up, now this begins to look familiar, right? This is exactly like what we have in the CNN. So this guy over here is going to look at an elliptical region here and the corresponding elliptical region in every C plane in that layer. Okay? And then you have the next S layer and the next C layer and so on. So the distinction was that the C layers only looked at the S, but the S looked at each C layer looked at only at a single S. Each S looked at all of the C's in the previous layer, right? Now, what about the responses themselves? The response of the S neurons had this he proposed this very complex function, but if you look at it really closely, it just looks like a ReLU. You have a weighted combination of all of the values within the ellipse, and that goes through a threshold which has a ReLU-like structure. The C cells are also ReLU-like, but with an inhibitory bias, in the sense that you need the total response within that ellipse to exceed a threshold which is not 0 before it begins firing, right? So, but then it turns out that you can actually kind of replace these two strange functions with a ReLU in the upper layer and a max in the lower layer, and the whole thing just still works. So what we've done is we have what Fukushima did was to propose a network structure. Now, as you go deeper in the layer, the deeper you go into these layers, the larger the receptive fields for each neuron. And there's a reason for this, that because the C cells are sort of voting across or looking at each neuron in the C cell is looking at a group of neurons in the S plane. Each C plane is actually smaller than the corresponding region in the S plane, which means that any point over here is looking at a region in the C plane, which is looking at a larger region in the S plane, which is looking at an even larger region of the retina. So as you keep going deeper through this network, the receptive field of each neuron on the retina keeps getting larger and larger in this original model. And another thing that happens is that as you go through the layers, the number of planes within each layer keeps increasing. This was again Fukushima's original model. The idea is that as you begin recognizing more and more complex patterns, then more and more complex patterns to recognize. If you're looking at lines of certain orientations, granularity of 15 degrees, how many different lines can you find? It's 180 divided by 15, whatever it is, right? On the other hand, if I begin looking at shapes that I can compose with these lines, I can find many shapes. So as you go deeper into the network, you need to be able to detect more and more complex patterns, so you have more and more of these planes. And he also came up with a learning algorithm for this. So this is what this model was called, the neo-cognitron. The neo-cognitron was because he first came up with a model called the cognitron, then he improved it, so this was the new cognitron, but call it neo, right? So this was the neo-cognitron. And the learning was completely unsupervised. You would randomly initialize the C cells, the S cells. C cells, of course, have a fixed response. They're just looking, there's nothing to learn on the C cells. And then you use a very simple Hebbian learning. So if the product of, if each weight is incremented by a value, which is simply the product of the input to the weight and the output of the neuron that it actually connects to, right? So specifically, he introduced some curious rules. Instead of drawing all of these planes vertically, like so, if you stack them up, he said that within any layer, at any position, only the maximum S from all the layers is selected for the update. So if I stack all of these guys like so, here I have 5 of these layers, right? So at any position, every one of those 5 layers has some response. One of them has the largest response. So I'm only going to choose that layer, and for that particular position, I'm going to switch off the rest of the guys. And that position is the only one. So the weight connecting to that position is the only one that I will update. But once what this means is that only one of the planes picks up any feature. But if I go across the planes, at each position you may end up picking a different plane. So when you go across the planes, eventually the entire planes get populated and all of the weights get updated. And if you find that multiple max selections happen on the same plane at any one point, you'd only pick the largest. But then, because you're using a Hebbian rule and you picked one point, any update that you make to a neuron over here, you're going to reflect that and copy those updates to all the neurons in that plane, right? So very simple update rule, nothing fancy. And here's what he found. He found that different planes learn different features. Any plane would only learn one particular feature. So given many examples of the character A, the different cells in the cell planes in the SC layers may learn patterns like these. The first layer may learn those strokes. The second layer begins learning more complex structures. The third layer begins to learn the actual characters and so on. And because you have a winner-take-all strategy when you're learning, which means that of all the planes, you're always picking only one plane to update. The whole thing has made it quite robust to distortion. But the key thing was this was completely unsupervised. He was trying to model the human eye, right? So how does our brain learn to respond or recognize different things? So he had this nice computational model based on Hubel and Wiesel's paper. And he showed that if you just gave, in his structure, if you just gave it lots of examples of characters, say even in noise, and then just run this and this unsupervised training all the way through, if you looked at the final layer, you'd find that the individual planes had learned the individual characters. So for example, it might learn from all of these. It might learn, if a neuron in the neurons in the final layer might individually fire in response to the digits 0, 1, 2, 3, and so on, or to characters. So all very fine, right? What he has come up with, what this model did was to come up with an unsupervised learning model that sort of attempted to emulate the computations that might potentially be happening in the visual cortex. And the whole process was unsupervised. It's still not very useful for performing real pattern recognition tasks. To make it perform pattern recognition tasks, we have to add one small bit, which is supervision. And so a neocognitron is fully unsupervised. The semantic labels are fully automatically learned. Can we add external supervision? You had various proposals for adding external supervision. The earliest one that I could find was by Homer Atlas and Marx in 1988, which was looking at a temporal supervision, trying to recognize time series data. Then Kevin Lang, etc., et al. Came up with time delay neural networks once again. This is temporal supervision, right? And then, of course, Jan LeCun came up a year later with ConNets in 1989. So Jan LeCun was actually the last to the scene in this particular, they're all more or less the same time. But if you had to set dates on it and look at the papers, 1989 is, I think, when LeCun's paper came out. But here's what we're really doing. So you have this entire thing. This whole structure is completely unsupervised, right? Now, we have no idea what the final output is going to be because it's unsupervised. Suppose I want to make it recognize a specific thing, like a digit. What do? I can just give it a signal and say, what you found is what I really want, right? So you're going to find, for example, if I'm trying to make it recognize digits, I can just give it a signal over here whether what it has found are really the digits or not. You provide supervision. And now you can go back and learn the rest, actually learn the network. And now you have a fully feed-forward multi-layer perceptron with shared parameters. Why do I call them fully feed-forward multi-layer perceptrons? Because in Hubel and Wiesel's model, which is where this whole thing originally began, you had an S-plane. Within S-plane, you had many neurons. But all the neurons shared the same parameters, which meant that if you updated one of them, you updated all of them. But you explicitly, physically had many different neurons as a plane for each plane, right? So this whole thing is just a simple multi-layer perceptron. And you can use backpropagation to train the S cell weights. You're not going to be training the C cell weights, right? Now, once again, remember, the S cell was actually responding to inputs from the previous layer. The C cell was simply performing a max over groups of cells from the S layer, right? So note that the original neocognitron actually uses many identical copies of a neuron in every S and C plane. So this goes back to what we were saying in the last class. The structure that the whole model was built upon was literally built upon multi-layer perceptrons of neurons with shared parameters, right? Now, in LeCun's approach, he replaced this elliptical receptor fields with square receptor fields. So the receptor field of an S cell in the Lth layer would be some KL cross KL, and the receptor field of the corresponding C cell is going to be some, L, uppercase L, well, LL cross LL. I need a better notation than that. And the specific response that you're going to find, this is for the S cell. The response of the S cell in the ijth position is going to be for some activation sigma, which we saw was best model in the case of the neocognitron. This was the activation that best captured the spirit of the model was the ReLU. In LeCun's case, instead of using the ReLU, he actually used a sigmoid, and it works on a weighted combination of inputs. So basically, you are looking at the weighted combination of all of these guys. The weighted combination of all of these guys in every layer, except that those receptor fields are now ellipses. So you'd be summing across all of the previous C planes. Within each C plane, you're going to go at each position ij. You're going to go across a little box around that ij and compute a weighted combination of all of the pixels within the box across all the planes, right? And then you apply the activation on that weighted combination. So this was the S plane. And for the C plane, you would now look at a box and just pick the largest value. So again, we are sticking true to the original model of Fukushima's model. You have the weighted combination and activation followed by the max, right? So, and then of course you can now observe that having many identical neurons is exactly the same as scanning with a single neuron, which is basically what LeNet did. So the scanning was more a computational artifice than a fundamental feature of the model, right? The fundamental model itself, if you go back and look at Fukushima's model, is that you have many copies of the same neuron, which is exactly the same as scanning with a single neuron, as we saw in the previous class. So LeCun's LeNet, as we saw, was actually LeNet 5. This is from LeNet 5. Was used this architecture and was actually able to do a really nice job of recognizing handwritten digits. This is the MNIST, I believe, right? So, you can find this demo on his website. As the images come in, it actually recognizes the digits quite accurately. And observe the position invariance. As the digit begins to slide in, at some point it begins to recognize it and continues to recognize it as it slides all the way out, right? So here's the general, this was a convolutional neural network. It's convolutional simply because you're using convolution to produce each of the S and C maps. Other than that, it's exactly the same as Fukushima's original model with supervision, right? So a convolutional neural network comprises convolutional and downsampling layers, and the two may occur in any sequence, but typically they alternate. So you have the S-plane equivalents, which are the convolutional layers, followed by the C-plane equivalents, which are taking essentially finding the strongest response in small regions of the previous S-plane to clean up the output of the S-plane. But not every S-plane needs to be followed by a C-plane. So the S and C planes can occur in any order, except that there's no sense in having multiple C planes, right? So you can have an you have a sequence of S planes, convolutional planes, with these max pooling C planes occurring intermittently between them. Now, and here is the overall structure. So the first layer would be looking at the input image. Then you'd have this downsampling layer. We're calling the downsampling layer because each pixel over here is actually looking at a group of pixels in the previous convolutional plane and picking just one of them. So as a result, an entire group becomes just one pixel. So it's a downsampling layer. Then you have a convolutional layer where each pixel is looking at regions, entire regions of all of the planes in the previous layer, followed by another downsampling layer, and so on. This can continue to happen. And you may even have multiple convolution layers without a downsampling layer between them. Right? At the end of it all of these outputs are sort of flattened into one single big layer which are just fed to a multi-layer perceptron. So this was the basic general architecture of a convolutional neural network. The convolution layers are learnable. Their parameters must be learned from training data for the target classification task. Downsampling layers are generally fixed and they're not learnable. So the convolution layer, again, all of this will look familiar because we've just seen how convolutional networks were built up in the last class. Comprise a series of maps corresponding to the S-planes and the neocognitron. They are variously called feature maps, activation maps, or as some of you have discovered in your on Piazza channels. Okay, so you have the previous layer. These previous layer contribute to providing all of these maps, right? And each activation map over here has two components. The first is where you compute a weighted combination of pixels or in all of the maps in the previous layer to get a single value. So this is performed by the convolutional filter, and that is then passed through an activation. So you have two components. This is computing a weighted combination, and then you perform and then you compute an activation on it. So it's a two-step process, just like a standard perceptron, right? So the one key piece again is that all the maps in the previous layer contribute to each convolution, right? So let's consider the contribution of a single map. This is what is a convolution. So let's say I have this map, and in my case, I'm just assuming for this example a simple binary map where every pixel value is 1 or 0. And let's say I have a filter which is like one of these perceptrons, one of these neurons in the convolutional or S-plane, right? So it's going to have a rectangular receptive field on the previous layer. So the rectangular receptive field, if it's 3 cross 3, it's going to have 3 weights. But then don't forget this. This is a standard perceptron. It also has a bias. So it's not just weights. It's a weights plus a bias, right? This is just a perceptron. So the output at any position, which is the contribution of just one map, okay, is going to be, let me put it this way. You would, to compute the output at any particular position, you'd put the weight on top of the corresponding location of the image, do a component by component multiplication, add the lot, and then add in the bias, which in this case is 0, and here you're going to see the answer is going to be 4, right? So at each location, the filter and the underlying map values are multiplied component-wise, and the products are added along with the bias. So I can keep moving forward. This is what you get in the first position. This is going to be the second position, the same weight, the same pattern, right? It's looking at a slightly different portion of 1 pixel shifted portion of the image. Then you'd go down to the bottom. So again, it's the same weights, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Again, with those weights, you have a component by component multiplication. You add the lot, you add in the bias, and you get that third number. One more, and you get the fourth. And so you can actually scan the entire image to get the map. So now, again, we actually compute any individual convolutional map from all of the maps in the previous layer. So if we actually modify our visualization a little bit, you will see exactly what I mean by this. Instead of drawing all of these maps one on top of the other, let me stack them up like so, right? So if I stack them up like so, now your filter is not just a rectangle. Your filter is actually a tube, a rectangular tube, right? So it would be something like this. All of your maps are stacked, and there is going to be a bias. Do not forget the bias. And so we can look at the joint processing of the various maps as processing the stack using this 3-dimensional filter as follows. First, you'd stick the filter in the top left corner, and you'd basically be performing the same component by component multiplication and addition, and then finally add in the bias to get one value in the resulting map, right? And then you'd slide one step forward, so that whole thing is going to give you just that one thing, right? One. Then, and so this is the contribution of the first map, this guy here. This summation here is the contribution of just that first map. And then I'd be summing over all of these guys, and I'm going to be getting the contributions of all of the maps. And this was a question that also came up in Piazza. Observe that this is a cube, right? the filter is a cube. All values within the cube are different, which means that these weight values which are being applied to the first layer need not be the same weights that you're applying to the second layer or the third layer. The weights are all different. It's just a cube of weights, right? And then once you compute this value, you can slide this one step forward like so, and get an output. So now the filter is working on the entire collection of stacked maps, but the output is just a single two-dimensional surface. That's because you have a two-dimensional scan, right? So although the filter is three-dimensional and it's working now on effectively a three-dimensional object, the output is still just a two-dimensional scan. You'd have many such filters, each of which is going to produce an output map of this kind. Okay. Now, something about the size. So let's say the image size is 5 cross 5, and the filter is 3 cross 3. Now the filter can move over one pixel at a time, or it could be jumping, when you're scanning it, you could be jumping more than one pixel at a time. How much you jump by is what we will call the stride. So if I have a 5 cross 5 image and a filter that's 3 cross 3, what is the output size going to be? Now this is questionable, right? Now if I want to stay strictly within the bounds of the green box when I'm scanning with the yellow filter, like so, then for each position I'm actually going to be using 3 of these guys, right? When I get to the extreme, wait, this should have been 3 cross 3, right? So what happens is that when I get to the extreme right, when I get to this position, I have no more image to the right. So if I try to scan further, I'm going to fall off the image. The outcome is now, although the original image was 5 cross 5, the image is only going to be 3 cross 3, right? Now on the other hand, if I were scanning by a stride of 2, right? In this case, I'd have my first filter here, then I'm going to jump by 2 pixels, which is this location. Then I can stride no further, because if I go further, I'm going to fall off the edge. And now the result is going to be a 2 cross 2 image. So the point of this is that although I start with a large image, every time I scan the image, because I don't want things to fall off the edge, the result is actually going to be smaller than what you began with. So in general, if you have an n cross n image and you're scanning it with an m cross m filter, and if you have a stride of 1, what would the output size be? So this is going to be, you're going to move till you can no longer fall off, right? So that means you're going to have, if it's n, then the width of the filter minus 1, that's how much you're going to have to chop off from the end, right? Because you eventually get to a position where moving the filter even by one position goes off the edge of the board. So in that case, if you have a stride of 1, that's going to be n minus m minus 1, right? Along each dimension. If you have a stride of s, what would that be? Just help you, right? So that's going to be, it's the same thing. You can imagine shrinking the entire image by a stride of s to begin with and having a stride of 1. So that's basically, that's a kind of, instead of trying to work out more complex arithmetic about what happens when you stride, shrink your original image by the stride, and perform your computations, you get the answer, right? So, but you get the idea. This is actually going to shrink. Now, this results in a reduction in the output size even if s is 1, and sometimes people don't consider it acceptable because you want the image to stay, when you're not actually actively downsampling, you like the image not to become smaller. So there's a standard trick that you would apply. You pad zeros all around so that when you actually scan it, the result is still the same as the size of the green patch. And how many zeros would you actually pad? You're going to pad as many columns as required to make the output of the green patch, and you're going to try to make it symmetric. So for example, if your filter width is size 5, you're going to lose 4 layers. So you'd pad 2 columns of zeros on either side, and similarly 2 rows of zeros on top and bottom. If your with this filter is width 4, you're going to lose 3 layers, right? 3 columns. So in which case you're going to put 2 columns of zeros, one on one side and 1 column on the other, and so on. So if you do this, the result of the convolution is going to be the same size as the original image. Now, again, convolutional image networks are in fact equivalent to scanning with an MLP, right? So you could just run the entire MLP on each block separately and combine the results. Now, even computationally speaking, scanning with performing this convolution and simply scanning the entire image with an MLP, the two perform exactly the same number of computations. There's really no difference. The number of additions you perform is the same. The number of multiplications you perform is the same. The number of times you actually compute the activation function is also the same. So it doesn't really matter which way you think about it. Thinking of it in terms of convolutions is actually more a business of computational efficiency. If you've got large enough filters, if you perform convolutions can be performed in the transform domain to reduce the amount of computation quite a lot. But if the filters are small, this doesn't really buy you anything, right? So as a result, you could be doing things either way. Again, performing things as convolutions is more a computational thing than a fundamental structural characteristic of the model. So this is something you must keep in mind. There's nothing magical about convolutions. You're still just applying a large MLP with shared parameters. Okay. Now, the other component was the pooling, right? Convolution and activation layers are followed intermittently by downsampling or pooling layers, and they usually alternate with the convolution layers, but this is not necessary. So max pooling selects the largest from a pool of elements. We saw this in the previous class. And pooling is formed by scanning the input. So you'd look at, for instance, those 4 pixel values, pick the largest one. And you can do this scanning left to right, exactly as before. Now, during the scan, if you had a stride of just 1, you're going to end up again with an output which is approximately the same as this same size as the input. But that, if you go back to the original neocognitron model, that was not the objective. In the neocognitron model, the C planes or the max planes were actually downsampling stuff to make things smaller, such that downstream neurons had larger receptive fields than upstream neurons, right? So again, a lot of the modeling that we actually perform in convolutional neural networks actually goes back in its motivation to the Fukushima model and to Wiesel and Hubel's model from the late 50s, early 60s. There wasn't a whole lot of additional computational thinking about these. That has happened more recently. People questioning why we even need to mimic those processes and why we cannot do things differently. So in the original model, the max operations would stride by the width of the max itself, right? So an n cross n picture compressed by a p cross p max pooling filter with stride d would result in an output map of n minus, effectively n over d, because you're going to be downsampling by the stride. And there's some fine detail over here in the exact size, which is going to be n minus p over d plus 1, right? And typically when we perform max pooling, we don't zero pad for a very simple reason that you're trying to reduce the size of the image, and those zeros can actually muck up what you get, right? Now, you don't need to perform max. You could be performing other kinds of operations. So instead of computing the max, if downsampling is the objective, then you could just be performing mean pooling, meaning instead of taking the maximum of all of those values, you could be just taking the mean. And the mean has a nice characteristic. The mean is a differentiable operation, the max is not. Or you could be doing something even more different. You could be computing a p-norm. This is also fairly standard. A p-norm, now remember that if I take the max of a and b, this is the same as a raised to n plus b raised to n through, let's say, right, do I even need 1 over 2? 11, 10, 10, 7, right? So this is going to be like the infinity norm. So instead of using p, let me call this p. So instead of using an infinity norm which is not differentiable, I can actually use a smaller value of p, which gives me the p norm pooling, which is going to be slightly different from the max. It won't be actually, the max value is going to be slightly less than the max value, but now this is a differentiable function. Or instead of having a fixed response, you can actually use a fixed network which looks at those 4 guys and figures out what the output must be. The only point is that this network is fixed. You're going to use the same network. You're effectively scanning with this network, just as you were scanning with the max operation. And so now the max or the mean or the p norm is being replaced by a network in itself. They call this a network in network, which leads to and now the network can be learned, which leads to the next obvious thing, right? Why even bother? Just replace the max pooling or the pooling layer with another convolutional layer. Because once I begin deciding that I'm going to be scanning it with a network that I'm going to learn, that's just a convolutional layer, right? So the latest thing that you might have done in your homeworks is the all convolutional network, which completely dispenses with this business of max pooling or pooling of any kind. Instead, you have a convolutional layer with a stride that's greater than 1 to shrink the size of the layer, right? Now, these are all just straightforward mathematical extensions of the basic idea that you started off with this notion of max pooling, which was hypothesized by Wiesel and Hubel, kind of formalized by Fukushima, and fixed, computationally modeled also by Jan LeCun. There was an unlearnable layer, and then we waited several years to say, hey, why have something that can't be learned? Why don't we just learn it? At which point the layer just goes away, right? Anyway, so let's put all of these pieces together. Here's a typical image classification task, assuming max pooling. Look at the time. It's you'd have an input. And the input is going to be 1 or 3 images, depending on whether you're working with a grayscale image or a color image. If you're working with a color image, you're going to have R, G, and B. So it's 3 images, right? If somebody gave you an image in any other color image in any other kind of color representation, you typically convert it to RGB. Remember that images can be represented in many different ways: CMYK, YIQ, and so on. So you convert that to RGB, because the assumption is that the different colors carry different information. And now, so here's the input, which comprises 3 pictures. You stack them up. So now it's a cube, right? And typically, we work with square images, or used to. These days, we're getting more flexible. And if you're going to be working with images of any kind, then you're going to end up with a large network. Too much detail. You need very big networks, especially towards the end when you get to the flat layers. So you typically scale these things down to 32 cross 32 or 128 cross 128. At least in the early days being just a couple of years ago, right? And so here you'd have an initial input stack of three pictures, R, G, and B, which is an I cross I image. And then you'd have a bunch of different filters. Let's say K1 total filters for the first layer. Each of these is going to be some L cross 3 filter. 3 is the depth because you have R, G, and B. The span of the filter is L cross L, right? So filters would typically, K1 would typically be a power of 2. These were just somewhat arbitrary choices. Where they come from is unknown. Some of it is religion, some of it is empirical. Mostly it's religion, okay. And filter sizes, 5 cross 5, 3 cross 3, 1 cross 1. So what is the strange, now why 5 cross 5? These are small enough to capture fine features. And this is particularly important for scaled down images, right? So you want this to be really small. And what is a 1 cross 1 filter? Yes. Which one? Pardon me? 1 cross 1 is, that is it. That's all it is, right? You're going to be looking at those 3 dimensions. A 1 cross 1 image is basically now a single perceptron which is going across the depth layer, right? And you'd be scanning with a single perceptron. So there's no longer a filter which is looking at a patch. You're just looking at a perceptron which is shrinking the collection, which is collapsing the different dimensions into a single dimension, right? So you'd have K1 such total filters, and if you want a better notation, the better notation is going to be not just 5 cross 5, but 5 cross 5 cross 3, where the term cross 3 within the parenthesis shows you the depth of the filter, but the 5 cross 5 shows you the 2 dimensions along which it's going to scan, right? And the number of parameters here you'd have to choose is how many filters, what is the size of the filter, right? And what is the stride. And again, keep in mind that each filter is going to be L cross 3 and a bias. Never forget the bias, right? So the total number of filters is going to be K1 times 3L squared plus 1. The one is, of course, that each filter has its own bias, right? And typical stride is 1 or 2. So once you process this, and you may or may not zero pad, depending on whether you want to keep the size of the image or not. But once you process the whole thing, here's the processing. For each filter, you're going to be going across all the colors at each position and across the area of the filter, and you're just computing a weighted combination of the images on each of the 3 planes within the area that the filter is looking at, right? And that's going to give you the weighted combination Z, and then of course you apply the activation, whatever you choose it to be. Typically we will use ReLUs because they provide the best response, or some variant of it. In Jan LeCun's original paper, these were sigmoids. And so now you end up with a bunch of maps, one from each filter, right? Now you can, the first convolutional layer has K1 filters, each of L cross L times 3. The spatial span is L cross L, the depth is 3. So you have these many parameters, and all of these parameters must be learned, okay? Then subsequently, if you were to perform a max pooling, each of these guys is going to be shrunk by a max pooling operation, which is a downsampling operation. So if you started off with an I cross I image, assuming that you're not going to shrink it, you have some zero padding, these are all going to be I cross I. Then if you max pool with a stride of D, they're all going to shrink to I over D cross I over D, right? So the parameters for the max pooling block the max pooling are what is the size of the max pooling block and what its stride is going to be, right? And the other choices are whether you really even want to perform max pooling or do you just want to learn the whole thing. In our homework, we actually didn't bother to learn any max pooling, we just learned it, right? So now, just for the operation, this operation is a 2-step operation. First, within each max pooling block, you find the position of the largest value, right? So you observe that from each of these guys, each element over here is looking at a small region over here. So the first thing you would do is to find the position in that small region where the largest value happens, and then you're going to read that value off, and that's what you will store. Now, finding the position and reading the value are 2 independent steps that you must keep track of. And then once you've done that, you can stack the whole thing up. You have the next set of filters, which will have some different set of parameters, which is going to give you a bunch of output maps. You'd perform a max pooling on those, and with how many other parameters, right? You'd perform a max pooling on those and shrink those and repeat the whole process till eventually you came to a multi-layer perceptron, which gave you your output. So this is the standard structure, the way the whole thing works. Now, each convolution layer maintains the size of the image if you zero pad it, otherwise it shrinks it a little bit. Each pooling layer actually shrinks it considerably by the size of the stride itself. The filters within a single layer must all be the same size. So for example, there's no reason this must absolutely be true, but all of these filters, for example, will typically be the same size. They're all going to be L cross 3, right? But filters across different layers could be different. So the L in the first filter could be different from the L2 for the second filters. And in general, the number of convolutional filters is going to keep increasing as you go through the layers, because as you go through the layers, you expect to find more and more complex patterns, and you expect to see more and more complex patterns that you can compose from the simpler patterns of the lower layers. And so the design choices are generally the number of filters and parameters. I'll skip over this. So here was a typical setup for Jan LeCun's digits classification task. It started with a 32 cross 32 image. The first layer had 4 filters, then the second layer had 10 filters, and then you had the MLP. So you had only 2 convolution downsampling layers. And the filters here were all 5 cross 5. There was a 2 cross 2 subsampling, then there was another 5 cross 5. There was a 2 cross 2 subsampling, and then you had the final MLP, right? So now what about learning? You have this entire structure. How does one actually perform learning? Learning is very simple. It's straightforward backpropagation. So the parameters to be learned are the weights of the neurons in the final MLP and the weights and biases of every filter in this entire chain, right? So if you were to perform backprop, in the final flat layer, all the weights and biases of each of the perceptrons must be learned. In the convolutional layers, each of the filters must be learned. So just some numbers. I'm running out of time, so I won't go over this. But here's the manner in which the actual training happens. It's exactly as in the case of the MLP. You're going to have backprop. The only difference is in the structure of the network. So you're going to assume that you have training examples for images and their class ID. We define a divergence between the desired output and the true output of the network. And the network is trained using a variant of gradient descent, where the gradients are computed through backprop. So in the first step, you could just use straight up backprop, and you could compute the gradients of the divergence with respect to the weighted inputs to all of the neurons in this layer, right? You could also, in the process, compute the gradients of the divergence with respect to the weights in the flat layer. And then, subsequently, you can perform backpropagation going all the way backwards. You need some adjustments over here, and the adjustments are twofold. Firstly, if you're using max out, you need some adjustment for the pooling layers. For the rest of them, you have shared parameters, so you have to worry about the shared computation. So in the case of the max out, remember what we did was at each location we found the position of the max, and then we read the value of the max, right? Now, the derivative of the output of the max out cannot be computed in regular backprop, but we can compute it backwards. We can sort of pass it backward to the appropriate pixel value in the previous layer. So if you're doing a max out, the max out itself is a fixed filter. There's nothing to learn. The problem here is that max and argmax are not differentiable, right? So what we will do is come up with an approximation. We're going to say that the derivative of the divergence with respect to the input to any max out filter is going to be simply the derivative of the divergence with respect to the output if that pixel has been selected as the largest value. For the rest, you're going to assume that it's 0, right? Very straightforward. And the idea behind this is very simple. If it's not the largest value, varying it a little bit will not change the output in the first place, right? And for the weights, every weight contributes to every position in the map at the output of the convolutional layer, right? So what do I mean by this? If I look at this weight over here, because the filter is scanning, right? If I look at any position at the output, that position, so if the value at that position has been obtained through a scan, which means it has contributions from many different positions in the previous layer. So it has every pixel value has contributions from every weight. This is standard, right? The output of any perceptron is basically going to have contributions from all of the weights going into the perceptron. That's basically just restating it, except now things are shared. So this gives us a pretty ugly update rule where you have to figure out how things are shared and see and make sure that the gradients are accumulated over all of the terms that contribute to any particular output, or all of the terms that a weight actually affects. So I won't go over this. Take a look at this in the slides. So anyway, the point is you can actually compute the derivative of the divergence with respect to every intermediate output and every weight. And although I'm sort of skimming over the arithmetic over here, it's tedious, but it's not difficult. It's very, very straightforward. It's exactly the same as what you would normally do. And if you think of this as a shared parameter network and go back to what we said in the last class, you can just write out the arithmetic in a very straightforward manner. For training, you have all the standard convergence issues. In your homework, you're going to see all of these things. You're going to use tricks like RMS prop, batch norm. The issue, of course, is the number of parameters can get quickly get very large, and so you will have insufficient data to train these things properly. For images, we have various solutions like data augmentation, where you'd start off with some pictures, then you jitter them a little bit, like rotate them, translate them, rescale them, flip them. And doing all of these doesn't really change the label, right? So you can distort you can start off with a training instance, and you can modify these training instances. So here you have a bunch of training instances, and in this case, each of them has been distorted through a rotation or through speckling, but it still maintains the same label. So now you have synthetic data that you can use to augment your training data. And you have other tricks like very deep networks, things called ResNets, and so on. So anyway, so before I wrap up, let me just sort of go through some examples of how complex these things actually get. I sort of skimmed over some of the details, assuming you can go back and look at them in the slides. What I really wanted to get across was the complexity of the models, this very simple, that people have actually come up with using this rather simple formalism. Now, if you look at Jan LeCun's original model for image classification, he started off with a 32 cross 32 image. The number of filters was very small. You had 4 filters in the first layer. You had 10 filters in the second layer, right? So if you really looked at the number of parameters, you had 5 cross 5 times 4, which is 100 parameters in the first layer, right? You had 5 cross 5 cross times 10, which is 250 parameters in the second layer. So 350 parameters gave him the entire convolutional structure. And thereafter, he had a somewhat larger number of parameters down here, but he got a very good digits classification performance using this. But then now, and if you in this model, if you actually go and see what each perceptron learns, even in a simple model, you can actually compute these receptive fields, and you see that as you go deeper and deeper into the layers, you find that each of the perceptrons actually begins to recognize things that look more and more digit-like. So I think this was a 5-layer network where the final perceptrons end up looking like they're capturing digits. Anyway, let's skip that. So here is the actual structure that he had. So no, I had the numbers wrong. For MNIST, he had 6 5 cross 5 layers in the first convolutional layer. Then he had 16 5 cross 5 layers in the filters in the second convolutional layer. And then for the final MLP, he had a 3-layer perceptron with 120 neurons, 84 neurons, and 10 output neurons. So the total number of parameters, as you can see, is fairly small, right? Now, where things really begin to get interesting, when CNNs really began to take off, was when people realized that this could be applied to the ImageNet task. Now, these days, when you go on Google, they put in an image, it's actually going to label things for you. It's going to assign labels to your images. Just 5 years ago, it would do that, because recognizing objects and images was incredibly hard. And as a standard benchmark for this particular task, people had come up with the so-called ImageNet large-scale visual recognition challenge data. It was collected by, I think, Fei-Fei Li and her team in Stanford. The actual data set consists of millions of images downloaded from the web. Each of them was categorized, and these categories were arranged in some kind of an ontology. And about 1.2 million of these images were released as a standard test set for people to perform image recognition on. And there were 1,000 categories of images that you could recognize over these 1.2 million pictures. So prior to neural networks being used to these tasks, the typical performance on these things, it wasn't bad, but it would be like 25% error, meaning 25% top 5, meaning if you pick the 5 most likely classes for any image, then 25% of the time, the actual class would not be even in the top 5. Now, that's not bad. That's quite impressive, considering that you're looking across 1,000 categories, and you're looking at a task as complex as image recognition, right? but it was considered pretty good till along came AlexNet. And AlexNet had this really ugly structure when they first published it. This figure is very famous with its head cut off, and that's because this was how it appeared in the first paper, and then everybody copy pastes it from the first paper. So you see this 2-block image with the head cut off. Description of AlexNet. Now this complex structure again also had to do with the fact that they were using 2 GPUs, and they had to sort of split the computation across 2 GPUs. But the real point was this, that this was a convolutional neural network where the input was 227 cross 227 images. These are images from the ImageNet data. They had 96 11 cross 11 filters in the first layer, 256 5 cross 5 filters in the second layer. Then they had 384 3 cross 3 filters twice. And then in the fifth layer they had 256 3 cross 3 filters, and then 3 fully connected layers with 4,000, 4,000, and 1,000 output neurons, because you have 1,000 classes. So you observe that the total number of parameters actually gets to be quite large. Over here, this is 4 million parameters connecting these two guys. There's 16 million parameters connecting these two guys. And then the convolutional layers, of course, also have their own parameters. And considering that you're looking at millions and millions and millions of parameters that must be trained from just 1.2 million images, you would think this wouldn't perform very well, right? So they had 650K neurons, 60 million parameters, 630 million connections. They would train their network, but then it wasn't just sufficient to train. Now you also take advantage of the fact that classification is supposed to be shift invariant. So the image itself would be cropped in different ways and shifted around, and the same image would be classified multiple times, like so. For example, you might start off with this image, come up with different crops, and classify each crop differently, and then vote across the lot to get your final output. And here's what they got, which was, skip all of the details. The final top 5 error was 18.2% with just a single network. And if they used 7 such networks trained in parallel and combined their outputs, the error was down to 15.4%. This was huge because the best previous error was greater than 25%. So they basically reduced the error by about 40% from what was then the state of the art in a single, in just one paper, right? And that's when people woke up to the fact that CNNs can really be applied to these tasks, to image recognition. And that pretty much changed things. Then afterwards, of course, they also found that the features that you learn actually end up being meaningful. Let's skip that. You had other people coming on the scene, Zeiler and Fergus, just a year later. They came up with a more complex network with somewhat different structure, and they brought the error from 15.4% down to 14.8%. But the most complicated one of all was this thing called VGGNet, which shows you exactly how the research in this particular area goes forth, right? They tried dozens of networks with dozens of different architectures, ran experiments with all of these, and then picked the one which had the best performance, and that best one had 140 million parameters being trained, remember, from 1.2 billion images. But they managed to shrink that error down, top 5 error down, to 7.3%. Now observe that, note that two really strange things are happening. You're increasing the number of parameters in your network by orders of magnitude, way more than the amount of data that you have. At the same time, you brought the error rate down from 25% to about 7%, which is ridiculous, right? And then Google came up with something called Inception, which I never fully understood because it's really complicated, but it's some variant of ConvNets, and now that error is down to 6.7%. And the last one, where people sort of gave up on this task and said it's too easy, was ResNet, where now they have these networks. We'll revisit networks when we're talking about recurrent networks, which have hundreds of layers, 150 layers. So it's layer after layer after layer after layer after layer after layer after layer of convolutions with some additional corrections, which has to do with making sure that the gradients actually pass through. And now the error is down to less than 3.5%, right? This is on a 1,000-way classification task. So a random performance would be 0.1% accuracy, right? or 99.9% error. So now this is about 3.5, and I think the latest numbers are even better than that, right? Something below 3% or something. So which is at this at the current state of art, if you want to use ImageNet to publish a paper, you have to work really hard because the numbers are so good. So, but then CNNs are not just used for images, they're also used for other forms of data like speech, as you just found in your homework, right? We use convolutional neural networks, not just one-dimensional scans, but also two-dimensional scans, spectrograms of data to perform speech recognition. And we're doing 2D in the homework, right? So there's nothing magical about images. It turns out all kinds of data are amenable to this kind of shared parameter networks. So it's a standard in speech and several other tasks. So I'll sort of stop over here, rush through. But a recap, this CNN is a neural network with specialized connectivity structure. During the feed-forward phase, it's got convolutive inputs, nonlinearities, pooling, which might be optional. You can perform supervised training, and you can use standard backprop with some simple modification of the rules for the training. You have the simpler version where you have convolution in along only one dimension to give you time delay neural networks. Now I've skipped over a lot in the slides because I sort of wasted time talking about the cat experiments, but it was important to see where this whole model actually came from, right? But I suggest that you go back and look at the slides and go over all the stuff that I skipped, primarily because it's going to turn up in the quiz, right? So this is my trick to make sure that you see the stuff that I don't cover. Then we will have 5 questions on 5 of the topics that I've skipped, including the equations. So watch out for this, right? Any questions? None. Thank you.